Let's continue our look at angle theorems. So the next one was to do with cyclic quadrilaterals, and we know that the opposite angles in a cyclic quad are supplementary. All right, so here's the situation. So if I wanted to use this, I'd say, well, look, ABC plus ADC is 180, and the reason opposite angles in the cyclic quadrilateral, whether or not you're right equal to 180 probably doesn't matter, because I've already written it's equal to 180 on the left-hand side. But I mean, for completeness, I suppose I've put equals 180. Let's go and prove that one. So I want to prove alpha plus beta is 180. So I'll start up by drawing in a couple of radii, so CO and AO. And then I'm just going to use the theorem from yesterday with the angle at the centre being twice the angle at the circumference. So angle AOC would be twice alpha. But if I look at the reflex angle AOC, that one would be twice beta, because the reflex angle is standing on the major arc. And this is why it's better to say standing on the arc rather than the chord. Because when it's standing on the major arc, then it goes to the minor segment. When it's standing on the minor arc, it goes to the major segment. It's all right, but we also know those two angles must add up to 360 degrees, because angle is about a point or revolution angle. So 2 alpha plus 2 beta are 360. Well, alpha plus beta, therefore, is 180. So there's our proof for opposite angles in a cyclic quad. The other theorem we have to do with cyclic quads is the exterior angle theorem. Okay. So we have this sort of situation. And what we know is the exterior angle, so DCX, will be equal to the opposite interior angle. So in this case, BAD. I don't think I bothered with a proof for this one, but if you had to, it's fairly easy, because we just proved they were supplementary. But we also know these two angles are supplementary because they're angles on a straight line. Therefore, those two angles must be the same. Okay. Angles subtended at the circumference by the same or equal arcs, or chords, are equal. So this sort of situation. Now, notice it just says by the same or equal arcs. We most commonly see it when they're standing on the same arc. It doesn't have to be the same arc, though. So long as the arcs are equal, then that angle would have to be the same. So if there was another arc somewhere in this diagram the same as AD, then that angle would also be the same. In fact, if there was another circle, and we knew that other circle had the same radius, then an arc of the same length in that circle would have to have the same as well. But this is the classic one, so let's prove it. So this is what I'd write down first of all. So angle ABD would be the same as angle ACD. I write angles in the same segment are equal. Okay? But if you write angles subtended by the same arc, then it's probably safer to say angles standing on the same arc in this case. So they know, oh, it's standing on the major arc or the minor arc. Let's prove it. So I'm going to prove ABD is the same as ACD. Again, let's draw a couple of radii up, and we're going to yet again use the angle at the centre idea. So angle AOD would be twice ABD, angle at the centre, twice angle at the circumference. But then I could have said AOD is twice ACD. In fact, I didn't really need to write that reason down again. I could have just used ditto. Because remember, if the reason is exactly the same as the previous one you used, to save writing the whole thing out, you could just go ditto. Yeah? So therefore, ABD is the same as ACD. All right, so 9C.